In this video, I'm going to go through the solution to question 30 from the 2025 Australian Math Competition Intermediate paper. A 4x4 grid of unit squares is drawn on a whiteboard, and then some squares are shaded black so that no two black squares share a vertex. How many ways are there to complete such a shading? So, firstly, I want to bring your attention to the middle four squares here, right? Any two of these four squares is going to share this common vertex in the middle, which is why we can see that at most one of these central squares can be shaded. Because if we shade two of them, they're going to share a common vertex, which is not allowed. So at most one central square can be shaded. So we can split it into two cases and we can discuss whether one central square is shaded or none of the central squares are shaded. So our first case, case one, is that one central square is shaded. Okay. How many ways can we do this? Well, there are four central squares. So there are four ways to choose that central square. And again, by symmetry, for each of these four ways, there should be the same number of shadings. So just without loss of generality, I'm going to choose to shade in this one. Okay? I'm going to shade in the one on the top left. Let me do it over here. I'm going to shade in this one, and because only one of the central squares are shaded, I cannot shade any of the other central squares. What else can I say? Because of this square being shaded, none of the squares that share a vertex with it can be shaded. So everything around it must not be shaded. I'm going to use this cross to denote not shaded. So if we choose to shade this central square, everything around it cannot be shaded. And then we are left with this seven squares here. Let me just call it 1, 2, 3, 4, 5, 6, and 7. Okay. We can shade any single one of them. That's not going to affect anything with that shaded square in the middle. But notice something else. 3, 4, 5. They all share this vertex, right? So at most one of 3, 4, 5 can be shaded. So now I can discuss in different cases. 3 is shaded. If 3 is shaded, then everything that shares a vertex with 3 is not shaded. So 2, 4, 5 is not shaded, but we're free to shade 1, 6, and 7. So 1, we can either shade it or we can not shade it. There's two different ways to do that. And with 6 and 7, we can't shade both of them. But we can shade either one of them or neither of them. So there's three choices. Neither of them, 6 or 7. That's not going to share a vertex with 3. Okay, so 2 times 3. There are 6 different ways I can deal with that. Okay. Similarly, what happens if 5 is shaded? I can argue that there's also 6 just because of symmetry. If 5 is shaded, then 3, 4, and 6 are not shaded. I have two ways to decide whether 7 is shaded, and out of 1 and 2, I can shade neither of them or one of them, which is 3 ways. So 2 times 3 is equal to 6. What happens if 4 is shaded? If 4 is shaded, then 3 and 5 cannot be shaded because they share a vertex with 4. But then 1 and 2, they don't share a vertex with any other shaded square so far. So we can either choose to shade one of them or neither of them. So there's 3 ways. and 6 and 7 as well. I can shade one of them or neither of them. So that's three ways as well. 3 times 3 is 9 here. And what happens if none of them are shaded? If none of 3, 4, and 5 are shaded, then again, 1 and 2, I can choose whether to shade one or neither of them, and same with 6 and 7. 3 times 3 is 9. We cannot shade 3, 4, and 5 because that's the assumption. So, how many shadings are there? Well, we have to multiply by 4 because there are 4 ways to choose the central square. I might not choose this one. I could choose this one, or this one. And each of them, by symmetry, I can rotate the square around. And I can argue similarly, they have the same number of shadings, which in this case is 6 plus 6 plus 9 plus 9, what we've counted, which is 4 times 30, which is 120 in our first case. Okay, case 2, let's move on, is that no central square is shaded. If no central square is shaded, then I'm going to put cross, 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 cross. Nice. Now we're going to split into subcases. So firstly, our first case is if no corner is shaded. If none of the corners are shaded, what happens? Well, we don't shade any of these. What we are left with, these 8 squares kind of form a ring, like that. You can visualize that as a ring of 8. And what's so special about this ring is that any 2 consecutive squares in this ring is going to share a corner, as you can see there. And any 2 non-consecutive squares in this ring is not going to share a corner, like this one and this one. They don't share a corner, right? Because if I included these corners of the grid there, we have these and this and this is non-consecutive, but they share a corner, which is bad. So I got rid of the corners. In this case, we're left with a ring, and we're trying to shade some of these such that no 2 consecutive numbers of the ring is shaded. Okay? So, well, 0 shaded. Are we allowed to shade nothing? If we don't shade anything in this ring, then we're shading nothing at all. But it says here that some squares are shaded black. So when it says some squares are shaded black, at least one square is shaded. So we completely disregard that case. What happens if we shade 1 out of these 8 in the ring? I can choose any single one of them and it's going to work because there's no consecutives. So that's 8. What if I shade 2? Well, 8 choose 2 is the total number of ways that I can choose 2 of them. But then some of them are going to be consecutive, which I don't want. How many consecutive pairs are there? Because it's a ring, there's 8 different consecutive shadings, 8 pairs around the edges. 8 choose 2 is 8 times 7 over 2. That's 28 minus 8. 20. Okay. What happens if I shade 3 of them? Without loss of generality, if I shade this one, I cannot shade these 2. I can do this, right? There has to be at least one blank between 2 shaded squares, and we allow for 5 blanks altogether. So I can put the blanks in 1, 1, 3, and of course I can spin this ring around and put it in 8 different orientations. The blanks in 1, 1, 3. But I also can make the blanks 1, 2, and 2. This is a different configuration, and I can also put this into 8 different orientations around the ring. So there has to be 2 times 8. There's 2 different configurations. Just think about if 3 positive integers sum to 5, it has to be, and none of it has to be 1, 1, 3, or 1, 2, and 2. There's no other option. What happens if 4 are shaded out of the 8? Well, if 4 are shaded, it has to alternate between shaded and not shaded because no 2 consecutive can be shaded. It has to be either this way or you shade the ones that I didn't shade. So there's 2 different ways there. We can't shade possibly more than 4 because then we would have 2 consecutive. So the total number of ways in this case is 8 plus 20 plus 16 plus 2. 8 plus 2 is 10 plus 20. So there's 46 if no central square is shaded and no corner is shaded either. What happens if 1 corner is shaded? There has to be 4 ways to choose which corner, right? Okay. So we already assume that no central square is shaded. And we choose 1 corner to shade. So let's just suppose it is this one. At the end, we'll multiply by 4, so don't worry. Because we're not shading any of the other corners, we're not shading any of these. And these 2 squares, they share a corner with the shaded square, so we can't shade any of these either. What are we left with? Again, this is just a subset of that ring, right? Our 6 remaining squares that we can choose whether or not to shade, they sort of form a line. So I can shade just any of these I can shade or not shade. Now that I've shaded in at least 1 square, I don't need to worry about the none-shaded case because that only appears once. Okay, so out of these 6, I can't shade 2 consecutive squares. So if I shade none of them, that's just one choice. If I choose one to shade, I can choose any one of them. So there's 6 altogether. What happens if I choose to shade 2 of them? Well, 6 twos 2, but how many of them are consecutive? 1, 2, 3, 4, 5. Because it's not a ring, we don't have the first and last being consecutive, so we minus 5. 6 twos 2. 6 times 5 is 30. Divided by 2 is 15 minus 5, which is 10. What happens if I shade 3 of these 6? Well, I can choose alternating like this, but I can also put this one here. I can put these 2 like this, or I can just do this 1, 2, 3 like that. So there's 4 different ways. Okay, so what's the total number of ways? There's 4 ways to choose the corner. So I multiply by 4. And once we've chosen the corner, I have 1, 6, 10, and 4, which is 21 ways to do the shading. And I am left with 4 times 21. There's 84 different shadings if I don't shade any of the central squares, but I shade 1 corner. Now, if we shade 2 corners, we have to be careful because the 2 corners can be next to each other or they can be opposite. And they are different cases. So let's take a look at the opposite corners shaded first. Of course, there's 2 ways to choose the corners. because there's two pairs of opposite corners. So without loss of generality, I'm just going to shade in these two. And these two are not shaded. We're not shading in anything in the middle. That's the assumption of case 2 altogether. And I can't shade these four because, well, because they share a corner with the already shaded ones, right? What am I left with? I'm left with 1, 2, 3, and 4, where 1 and 2 share a corner, 3 and 4 share a corner. They're two different pairs, right? So how many ways are there to shade 1 and 2? There's 3 ways, right? I can choose to shade 1, I can shade 2, or I can shade neither, but I can't shade both because they share a corner. The same thing goes for 3 and 4, right? So 3 and 4. Oops. 3 and 4. There are 3 ways to choose that. Okay, so the total number of ways that I can choose, that I can shade if I shade opposite corners but none in the middle. There are 2 ways to choose which pair of opposite corners. There's 3 ways to choose 1 and 2, and 3 ways to choose 3 and 4. 2 times 3 times 3. That gives me another 18 shadings. Okay, I'm going to go over the page here. The next case is if we shade adjacent corners. Well, without loss of generality, let me just shade these two. Of course, I could have chosen these two, or these two. So there are actually 4 ways to choose the corners. There's 4 pairs of adjacent corners rather than 2. So there's already a difference there. We're not shading any of the middle squares. We're not shading anything that shares a vertex with these shaded squares. And we're not shading the other 2 corners either because we're only shading 2 adjacent corners in this case. Okay, what are we left with? Once again, this is a subset of that ring, right? We're left with 4. That goes in a line, and we have to shade. We can't shade consecutive members of them. So what happens if I shade none of them? That's one way. If I shade one of them, that's 4 ways because I can choose any one. And what happens if I choose 2 to shade? I can choose this one and this one. I can choose this one and this one. Or I can choose this one and this one. So there's 3 different ways. So the total number of ways in this case, there's 4 ways to choose the corners. And once you have chosen the adjacent corners, there is 1 plus 4 plus 3 ways. So 4 times 8, there's 32 different ways to do that. The next case is if we have 3 corners shaded. How many ways are there to choose the corners? There are 4, right? There are 4 ways to choose which 3 corners you're going to shade because 4 choose 3 is equal to 4. Basically the same as choosing 1 corner, but just whichever corner you choose, you don't shade it and you shade the other 3. Without loss of generality, I'm shading these 3. We're not shading anything in the middle, and these squares share a vertex with the already shaded corners, and we're not shading the 4th corner as well. We're going to deal with that in another case. So now we are just left with 2 remaining 1 and 2, right? And how many ways are there to shade these 2? There's 3 ways. You shade one of them or neither of them. So how many ways are there? There's 4 ways to choose the corners and 3 ways to do everything else. So there's another 12 shadings in this case. And our final case is if we shade all 4 corners. So we're not shading anything in the middle. And we're shading all 4 corners. Well, what are we left with? Well, all of the remaining squares actually share a vertex with one of the corners. So if we choose to shade all 4 corners, we cannot shade anything else. So there's only the one way to do it. Okay, so now how many ways are there to complete such a shading? We have to add up all the different numbers that we have here. So case 1, we had 120 if we shade one of the middle squares. And if we don't shade any of the middle squares, we have 46 if we shade no corners, 84 if we shade one corner, 18 if we shade opposite corners, 32 if we shade adjacent corners, 12 if we shade 3 corners, and 1 if we shade 4 corners. So what is that? 120 plus 46, 166 plus 84 is 250, plus 18, 268 plus 32, 300 plus 12 plus 1. So your final answer is going to be 313 possible shadings. And we are done.